The word quantum is a magnet for pseudoscience. From mystical crystals to alternative healing, the term often serves as a hollow marketing buzzword. Scientifically, however, it represents one of the most precise and rigorous disciplines in human history. To find its origin, we have to go back to the classical universe, a world defined by the physics of Isaac Newton and James Clerk Maxwell. In their equations, energy was a seamless, unbroken stream. Imagine a staircase without steps, a perfectly smooth ramp. In a classical system, you can occupy any exact point along that incline. There are no gaps in the motion, just as water seems to pour freely from a tap. For centuries, this continuous model worked. It predicted the movement of planets and the flow of electricity with such accuracy that it was accepted as the total truth of reality. But as technology improved, the math began to clash with observation. The first anomaly appeared in 1814. Joseph Fraunhofer, a German lens maker, used a high-precision prism to dissect sunlight. He expected a smooth, continuous rainbow, but found the spectrum was interrupted by hundreds of thin, dark gaps. These solar barcodes were the first sign that light was missing specific pieces. A second failure emerged when scientists studied blackbody radiation, the light emitted by a heated object that absorbs all incoming energy. Classical equations predicted that as the temperature rose, the object should emit light at every possible frequency. This chart shows where the logic failed. According to classical math, as light reached the high-frequency ultraviolet range, the emitted energy would climb to impossible levels, shooting toward infinity. This was the ultraviolet catastrophe. Reality refused to match the math. Real-world measurements showed the energy curve dropping back to zero at high frequencies. The physics of a continuous universe was incapable of explaining the light we can actually see. In 1900, Max Planck proposed a desperate solution. To fix the math of the ultraviolet catastrophe, he abandoned the idea of continuous energy flow. Planck suggested that energy is exchanged only in fixed, indivisible amounts. He called one of these individual units a quantum. This turned the smooth ramp of reality into a staircase. On these steps, you can stand on level 1 or level 2, but it is physically impossible to exist in the empty space between them. Albert Einstein expanded this idea in 1905 to solve the photoelectric effect, a phenomenon where light knocks electrons off metal surfaces. He proved that light itself is a stream of individual packets, which we now call photons. In this system, the frequency of light determines the energy of each individual packet. A high-frequency ultraviolet photon carries a larger, more powerful punch than a low-frequency red one. Light and energy behave like a hail of distinct, measurable projectiles. This discovery changed the way we understood the basic ingredients of the universe. This new logic soon moved to the atom. Early models pictured electrons orbiting a nucleus like planets around a sun. However, classical physics required an orbiting electron to constantly radiate energy. Without a new rule, every electron in the universe would lose its velocity and crash into the nucleus in a fraction of a second. In 1913, Niels Bohr saved the atom by applying the quantum staircase to the electron's path. Bohr proposed that electrons are locked into specific energy levels. They can only jump between these fixed rings. When an electron drops to a lower level, it releases a photon with a very specific color. This explained why Fraunhofer's barcodes existed. Atoms were only absorbing and emitting light at those exact staircase frequencies. Bohr's model was a breakthrough for hydrogen, but it couldn't calculate more complex atoms. In larger atoms, multiple electrons push and pull on one another, creating a chaotic web of interactions that the simple planetary model couldn't track. In 1927, the world's leading physicists met at the Solvay Conference to find a more sophisticated answer. Werner Heisenberg and Erwin Schrödinger replaced rigid orbits with mathematical probability. In this framework, an electron exists as a dense, fuzzy cloud. This cloud doesn't show a specific path, but rather the likelihood of finding a particle at a certain point in space. At the subatomic level, the solid certainty of our world is replaced by calculated odds. Reality, at its most basic level, is made of these discrete packets and mathematical probabilities. Quantum mechanics was born from necessity. Scientists were dragged toward these counterintuitive conclusions because the universe simply refused to behave classically. This discipline has a very specific domain. It is the physics of the ultra-small, the rules governing atoms, photons, and subatomic particles. These discrete, probability-driven rules are invisible in the macroscopic world. Our daily reality, the movement of falling apples and orbiting planets, remains governed by the classical physics of the large. Quantum mechanics is a rigorous mathematical blueprint. It is the structural logic of reality, distinct from the magic and superstition often associated with the name. Thanks for staying until the end. It truly means a lot. If this video spoke to you, like, subscribe, and ring the bell so you don't miss what's ahead. This is a space for philosophy, psychology, and science to expand the way you see life. Until next time, may wisdom walk beside you.